even if in half an hour. No, it's not going to happen. Okay, I started, yes. Okay, so the last section, 4.5, deals with applications. All models will be given to you. You do not have to memorize any of them. Okay, so there are a few models. One, the first two that we already know, which was A equals P times E to RT. RT. This is the model that we used at the beginning of chapter 4, and it deals with continuously compounded interest. Continuously compounded interest. Okay. Second one, we already know, is that A equals P times 1 plus R over N, everything raised to NT. It will be given to you, but this is interest compounded N times per year. Now the next three ones we have not seen before. Here is the first. Yes.
Sorry, isn't one of them where it's like you have to figure out how much, like with fossils, how much it decays after
Correct.
a certain amount of time?
That is one, the exponential say it again.
Half-lives.
Yes, the exponential decay. Yes. So the next one, the logistic growth model. The logistic growth model. You do not have to memorize it. It will be given to you. It's something that looks like this. You don't even have to write it. It will be completely given to you. Number 4, the exponential growth model. Let me be consistent and use R in all places as the rate. Do you see any resemblance? Just a couple of letters are different. Same formula. The exponential growth model, and the last one, the exponential. Yes, the last one. Decay model. And look at this. We're going to use M because it stands for mass. Do you see any difference between these two? This is the amount or number. This is mass. This is the initial amount. This is the initial mass. This is E. There is a minus in front, and there is the exponential decay rate and then time. So 3 models are the same. However, you're not supposed to memorize them. If you want to, you can, but I'm not asking you to. Okay, so we will review these when we get ready for the test or sooner, but we had problems like these before. So let's look at the logistic growth model and then the other two. And after this, and we practice as much as we can, this is the end of chapter 4. Okay. So let's start with the logistic growth model. Okay, let's look at 43 through 46 on page 531. P of x equals 90 divided by 1 plus 271e to negative 0.122x. And And in the exponential, in the logistic growth model, B equals 1, as you see it here already. Again, you do not have to memorize anything. The model will be given to you. Now let's see what it means, each and every one. I mean, the two variables, meaning p of x, the function, and x. Let's see what they mean. The logistic growth function is given. It models the percentage. Again, this is percent of Americans who are X years old. X is the age. With some coronary heart disease, with some heart problems. Use this function to solve exercises 43 through 46. I do have a friend who is, I think, 80 something. And when I was sick with that sinus infection, I called him once and I said, "Hey, Dennis, how are you doing?" And he said, "Well, how are you doing?" And I said, "Well, I'm this and that, and I'm not well, and I can't really get myself moving. I was very tired. I was very fatigued." And he said, "I know what you're suffering of." I said, "How do you know?" "Well, I'll tell you. You're suffering from AGE." I said, "What's that?" "Age." I said, "Really?" I said, "You are 80 plus, and you're talking about," "Yep, you're suffering of AGE." So, good. Okay, so here's the first question. What percentage of 20-year-olds have some coronary heart disease? So this is 43. What am I asked to do? Very good. 20 equals 90 over 1 plus 271 e to negative 0.122 times 20. Be very careful how you plug this in. It's not an easy situation. We need parentheses for the top, for the power. We need parentheses around the denominator. Luckily, we don't have any operations at the top, so you don't really need parentheses around 90. So let's do that. So 90 divided by, in parentheses, 1 plus 271. Careful now with e. In parentheses. On some calculators, it may work without, but some of you have an old calculator like I do, so you need parentheses for the power. Negative 0.122 times 20. Close the parenthesis for the power. Come down to close the parenthesis for the denominator. And only then press enter. What do you think? What would be roughly the percentage of 20 years old? Not too big, right? At the age of 20, the 20-year-old population should not have problems with their heart, right? So only apparently roughly 4%. So approximately 4%. It makes sense. Okay, 44.
Actually, the statistics at 35, you just be like that. So, yes.
Good. So what percentage of 80-year-olds have some coronary heart disease? What do I have to do now? Yes. So I have to find P of 80. Do not delete what you already have in the system, in the calculator, please. Just do this. With second and entry, it copies everything, and all you have to do is overwrite what?
20.
Yes, the 2 by an 8, that's all. And you press enter. So this must be higher. Yes, quite a lot. So roughly about 89% of the entire population, according to the model. And of course, it doesn't mean that everyone is in that category, right? So there are always outliers and so on and so forth. Okay, so roughly 89% of the 80-year-old population could potentially have heart disease. At what age? This is 45 now. At what age is the percentage of some coronary heart disease 50%? 4? Very good. Well, this is not an easy situation by any means. So this time we're given the percentage, and we're asked to determine X. What age group? Like my friend said, I suffer from AGE. So we want to find the AGE. Okay, so if you disregard this noise, because it's kind of a noise, right? You know what you're looking at. What are we looking at? If you disregard the noise in the denominator, then it's kind of poking your eyes. But you know what you have if you disregard that. It's a proportion, isn't it? Yeah. So that's how you have to look at it. It's a proportion, and we have to cross multiply. So 90 equals 50. Do not distribute. 1 plus 271 e to negative 0.122x. Now we got rid of the proportion, and I want to get rid of something else. Remember, we have to get to e. So slowly and slowly, I'm peeling off everything till I get to e. So what is the next peel?
50.
Yes, divide both sides by 50. That is the best thing. Can you distribute? Yes, of course. Is that an error? No. But it's easier if you divide both sides by 50. So I'm peeling off the 50. And to 9/5 equals 1 plus 271 e to negative 0.122x. Now, what am I getting rid of? Exactly, the 1 indeed. So I have to move 1 to the other side, and 9/5 minus 5/5 is 4/5. So the left-hand side is 4/5, the right-hand side is 271 times e to negative 0.122x. Remember, you cannot add 1 to 271. Why? Because 271 is multiplied by e. So you cannot separate these two. Okay, now what am I getting rid of next? 271, but it's easier if you say we are multiplying by 1/271. And you simplify these. You do not have to multiply these two. Just write 5 times 271 equals e to negative 0.122x. Now, this equation is what type?
Exponential.
Excellent. It is an exponential equation. It's all cleaned up. It's ready for
Calculator.
That was going to be my answer.
not yet. Correct. So this is a number and this is e. I cannot present both with the same base. But then what do? There is a technique that allows me to simplify. I apply something to both sides that allows me to bring the power down. Exactly. Exactly. Natural log, to be exact. The left-hand side is natural log of 4/5 times 271. Can anyone give us the right-hand side? Yes. Negative 0.122x. Don't bother with this. This is just a number. And finally, I get x. How? Exactly. This over this. Excellent. Thank you. Be very careful with this. Very careful. So let's do this together. Let's put in the graphing calculator together. Ready? The numerator is natural log. It's only one term, so I don't need parentheses outside. But it's 4 divided by a product. And I need the calculator to perform the product first. So 4, 5 times 271. Close the parenthesis for the denominator and close the parenthesis for the entire inside of the log. And now you can divide, and in parentheses, negative 0.122, and close the parenthesis. And press enter. So which AGE group? According to the model, about 50% of them. Yes, so X is approximately 48 years of age, years old. So yes, but be very careful, or you either multiply this, which I don't recommend. I don't want you to do too much and then copy. There is no need. As long as you're careful and put parentheses here and parentheses here, you're safe. Okay, final question on this problem. At what age is the percentage of some coronary heart disease 70%? Correct. And I think it's a good practice. I'll give you 2 minutes to reproduce this. So we want 70 equals 90 over 1 plus 271 times e to negative 0.122x. So let's work on this for 2 minutes, and I'll take attendance in the meantime. Anyone needs help? It's not a trivial equation at all. It has so many steps, and you have to think at every step. It's not boom, boom, boom. Okay, ready? So first I see a proportion, so I cross multiply. So I get 90 equals 71 plus 271 times e to negative 0.122x. There is a way of adjusting that, but I don't recommend that. Okay, I think it's better if we go through the steps again. So 9/7 equals 1 plus 271 e to negative 0.122x. Then I subtract the 1, which gives me 2/7. 271 times e to negative 1 to 0.122x. And then I divide by 271. 2 over 7 times 271 equals e. And now I can apply natural log. So the natural log of this, be careful with the denominator. You can multiply if you want to, if that's easier for you. Negative 0.122x. So then x will be natural log 2 over 7 times 271, negative 122. I prefer putting everything in the graphing calculator at once. But that's me. So all that changes is the 4 into a 2 and the 5 into a 7. There's nothing else. So this is a 7 and this is a 2. And I got 56 years old, roughly. So x is approximately 56. 56 years old. Any questions? Any questions? Did we get 56? Good. Any questions here? Do we understand this logistic growth model? We're not scared of it. All we have to do is maybe plug in something or and determine x in this case. Is that okay? Do you think we need another example with the logistic growth model, or we can move on to exponential growth? Okay, so one other thing I don't want to forget. So what you can do from this, first page already, second page already, third page, yes, fourth page, yes, fifth page, yes, sixth page, yes, everything. Seventh page, we just look at an example with the exponential, with a logistic growth function or model. Okay, and actually I would like to do this problem if you'd like right now or some. Yes? Okay, so let's do that problem before we continue with something else, with another model. So here it is. We are given f of t equals 110,000 over 1 plus 5,400 e to negative t. As you see, this is a totally different logistic growth model, but still the same. A number, 1 plus a number times e to something negative. The logistic growth function at right describes the number of people, so this is number of people, who have become ill with influenza t weeks, okay, t weeks, of course it's time in weeks, after its initial outbreak in a particular community. How many people became ill with the flu when the epidemic began? That is always original, initial, exactly. I have to find f of 0. So part A, f of 0. This we can do on our own without a calculator. Let me show you how. How much is e to 0?
1.
Very good. How much is 1 times 5,400? Good. How much is 5,400 times plus 1? Okay. Okay, so let's divide. Got 110. We do not round up people. So if you have 1.2, still you have 1. So this is 20 people. Although the answer is 20.3665. The 0.3 is not another person. Now if it's dollars, I would say 20.36, right? But if it's number of people or rabbits or whatever, bats, I can't. Okay. Even if I get 20.9, I will still say 20 because the 0.9 doesn't make another person. Okay, how many people were ill by the end of the 4th week? Good. F of 4. This I cannot do without a calculator from the very beginning. 1 plus 5400 times e to negative 4. Careful with parentheses. The top has only one number, one term, which is okay, but the denominator needs parentheses. So 110,000 divided by, in parentheses, 1 plus 5400 times e to negative 4. Close the parenthesis for the power and close the parenthesis for the denominator. And at the end of the fourth week, 1,101. 1,101 people. Final question here, and then we'll stop. What is the limiting size of the population that becomes ill? In other words, after the 5th week, the 10th week, 20 more weeks, 50 more weeks, 100 more weeks. So there are several ways here, but here's the easiest way. Let's put the function in the graphing calculator. 110,000 in y equals, divided by, in parentheses, 1 plus 5,400 times e, and the power in parentheses is negative x. Close the parenthesis and close the parenthesis for the denominator. And let's say, I'll show you another way next time. But since we only have 1 minute left, I don't want to hold you over. So I go second and table. This has a deep freeze. It always changes back to the default. Okay, so I'm going to say, okay, after the 4th week, I already know 11. What did I do? Okay, sorry about that. Second and table. Good. So after the 4th week, 1,101. Then I'm going to say after 20 weeks. Then I'm going to say after 50 weeks. Then I'm going to say after 60 weeks. Then I'm going to say after 90 weeks. And then I'm going to say after 1,000 weeks. What is the limiting size of the population that can get ill?
21.
Just the top, the numerator. What does that mean? As x increases without bound and increases and increases, and the function approaches 110,000, approaches 110,000, approaches 110,000, what does that mean? Horizontal?
Asymptote.
That's it. That's it. So C, as t approaches infinity, f of t approaches 110,000. Y equals 110,000, horizontal asymptote at infinity only. Very good. Any questions?